Sweet. All right. So yes, I'm going to talk to you about some progress that we did here at Sandia for performance portability of our ultra high resolution non-hydrostatic atmosphere model for E3SM. So some of you are very familiar with a lot of acronyms here, but I'm going to go over them at the beginning. So recap what's E3SM, HOMME, Kokkos, what's SCREAM, HOMMEXX. I'll show you our results, and then I'll briefly talk about EKAT, another acronym, which is a small library we're developing to support E3SM. So E3SM, most of you know it, but just in case, is the energy exascale Earth system model. It's a big DOE effort for a high-resolution Earth system model. It's modular with several components: atmosphere, land, oceans, sea ice, and more, which can all have variable resolution and usually go on unstructured grids, mostly written in Fortran 90. Broad variety of time and space scales. V1 was released 2 years and change ago. V2 is hopefully by next year, you know, the code freeze should be next year, but then when all the simulation campaign ends, we don't know. At least I don't know. What is HOMME? HOMME stands for High Order Methods Modeling Environment, is a component of E3SM and also CESM, which is the library that E3SM forked off from, which is responsible for dynamics and transport in the atmosphere. It's a very important part, computationally speaking, of E3SM. Typically accounts for about 20 to 25% of the total runtime of a fully coupled simulation. The library, the original Fortran 9 implementation, was highly optimized for MPI and OpenMP parallelism. HOMME features a decouple of horizontal and vertical differential operators. On the right, I'm showing like a typical computational element of HOMME. On the top, you can see a typical grid on the sphere. Each of those quadrilaterals is a spectral element. HOMME uses the spectral element method in 2D and either Eulerian or Lagrangian schemes for the vertical operators. So on the right, on the bottom, you can see the structure of the element. Each of those quadrilaterals that you see in the mesh at the top is then extruded vertically for a certain number of vertical levels, which is configurable. And each of those layers has, well, in HOMME, usually it's 16, but it's like n by n grid of degrees of freedom, which are the Gauss-Lobato points of the spectral element method, if you're familiar with that. So that's how HOMME grids look like. The last acronym, well, this is not an acronym, but it's a library, the Kokkos library that you probably heard before, has been mentioned in this workshop already. It's a library developed at Sandia in C++ that provides templated constructs for both multidimensional array abstraction as well as on-node parallelism patterns. This abstraction for the parallelism included execution space, the policy, and the operations, so the where, the how, and the what of the parallel executions. While for the view, the abstraction include the data type, the memory space, or the layout, the memory access, and more. Kokkos supports several backends, a serial one, which is no parallelism whatsoever, OpenMP, CUDA, HIP, and more. It's publicly available on GitHub. What is SCREAM? SCREAM stands for Simple Cloud Resolving E3SM Atmosphere Model. What is a cloud resolving model? Well, cloud resolving models usually have a horizontal resolution of 3 kilometers or below. They can do away with some parameterizations of some physical processes like deep convection because they can fully resolve them at the scale of their mesh. But they need usually more complex model for state equation, namely like non-hydrostatic rather than a simple hydrostatic model. SCREAM is the cloud resolving model that E3SM is trying to develop, targeting ultra high resolution. Our release is very optimistically for the first full C++ implementation is sometimes next year. That June 2021 is more of a deadline that tries to keep us on pace with our development. I seriously doubt we'll hit it. The target for the SCREAM will be a 3 kilometer horizontal resolution and 128 vertical levels. So that means that if you remember the element of home that I showed you before, there will be 128 of those vertical levels, and the average distance between two of those points inside the element will be about 3 kilometers, 3.2 actually. So that's amounts to about 7 billion grid points. HOMMEXX. So in 2018, we tried to convert the existing hydrostatic dycore of home, which solves for hydrostatic equations in the atmosphere, from the original Fortran 90 implementation to C++ using Kokkos for on-node parallelism. Our tasks try to maintain bit-for-bit agreement with the original implementation, at the very least in debug mode, with some specific flags for GPU. We tried to minimize architecture-specific code. That was the whole point of using Kokkos. Kokkos tried to hide some of the details of the underlying architecture and the threading model that you're using for parallelism. And we heavily tested it, and we had a reasonable success. So our implementation, on the right, I show two graphs that you can also find in the paper that appeared on GMD in 2019. On the top, we verified that our model was scaling, was performing as good as the original implementation on conventional architectures, meaning CPUs, KNL, basically. The solid line was our refactor using Kokkos, while the dashed lines were the original Fortran implementation, and you can see that we were at the very least on par with the original implementation and a little better on KNL for certain configurations. The second graph showed like a scaling study on a single node or GPU for different workloads, meaning basically different amount of elements on a single node or GPUs. And you can see typical patterns in performance for new architecture compared to old architecture. We tested various Intel CPUs from Ivy Bridge to Skylake. We tested GPU Volta as well as Pascal, and we also tested P9. So this is something that we did a couple of years ago, but the subject of this topic is the ultra high resolution, which requires a non-hydrostatic dycore, and a non-hydrostatic model, basically for the description of the state in the atmosphere. In home, this is called theta L, if you're familiar with home. So we did this task for the most part of for the second part of last year and the first half of this year. It led to a paper accepted as supercomputing this year, which should appear whenever supercomputing releases his conference proceeding. We used the same core design goals that we used in our previous effort for the hydrostatic core, which are fairly common across different projects. When you want to use effectively new architectures, what you have to do is expose as much parallelism as you can to fully utilize, especially the GPU. But of course, you don't want to lose performance on conventional CPUs or KNL, because we still have quite a few clusters that we still want to use for science experiments, and that means you have to vectorize really well, because that's the best way to exploit your architecture in terms of energy. And the third thing is, of course, minimize memory movement. Moving memory is expensive. The other two bullets are similar to the previous effort. We minimize architecture-specific code, and we obtain bit for bit with the original implementation, again in debug mode with a few. We had to take care of a few things, like, for instance, serialized reductions in order to get a bit-for-bit agreement on GPU. When you compare the new non-hydrostatic model to the original hydrostatic one, there's a few differences. Of course, there's model differences, like the non-hydrostatic model has two additional state variables. It uses potential temperature instead of temperature, but can run in both hydrostatic and non-hydrostatic mode. So in a way, it's a generalization of the previous model. There's a few additional challenges besides the original one of, like, exposing parallelism. vectorization and whatnot. There's two additional challenges, and one is the nonlinear solver, which I will talk again later, and then the larger memory footprint. We're solving like a much larger problem. We have more state variables, so there's a and due to algorithmic properties, we may have more temporaries to take care of inside our kernels. So I'm not gonna show any code. The code is public. If you're really interested, I can point you to it. But just to mention the results, we tested. Mostly we're interested on Summit, so V100 NVIDIA GPUs. On Summit, we also tested the Power 9s since they're there, so why not? And then we also tested on KNLs on the Core system at NERSC. On Summit, we scaled all the way up to 27600 GPUs, or 4600 nodes when running on GPUs. Oh, sorry, on CPUs. And on Core, we scaled all the way up, not all the way up to the full system size, but to 9200 nodes. So, okay, let's look right away at the most important thing that you have to achieve if you claim that you want to be a performance portable, which is scalability. So this is a graph showing our strong scaling results. We show both the original Fortran implementation as well as the new C++ implementation on 3 architectures, P9 and KNL for both Fortran and C++ implementation. And on GPU, we only show our porting of home. We also show a scaling study, which is the light blue one, for a finer mesh of 1 kilometer resolution, only on GPU, because on CPU the throughput will be completely pointless for practical applications. So on the x-axis, you see the number of Summit or Core KNL nodes, while on the y-axis, you see the simulated years per day metric, which is if I ran the code for a whole day, how many years in the simulation I would obtain. So as you can see, with GPUs, we're able to get a factor of about 10 to 20 speed up compared to P9 or KNL. When we scale to this full Summit system, we're achieving almost 1 simulated year per day. It's actually 0.97. In this model, we're solving for state as well as for 10 tracers. This is a benchmark, the NGPPS benchmark. Forgot to put the link if you're interested. We have an excellent scaling at 3 kilometer. It's not perfect, but I think it's excellent. And if you look at the 1 kilometer, it's perfect scaling on GPU. Our CPU performance, on the other hand, is still comparable or slightly better than the original Fortran 90. Remember, we want to be performance portable, meaning that on each architecture we achieve the best or a reasonable performance for that architecture. And as a remark, I put there the 1 kilometer resolution approximately features 1 trillion degrees of freedom, so quite the problem. So I mentioned there were 2 additional challenges in the non-hydrostatic solver. So I want to highlight some results that focus on those 2 challenges. The first one was the nonlinear solver. So home splits, as I said, horizontal and vertical differential operators. In the horizontal direction, it's explicit home, and the vertical direction is implicit. In particular, it uses a diagonal implicit Runge-Kutta scheme in the vertical direction, which we call also DIRC. The DIRC solver solves 1 nonlinear equation for each GLL point, so for each dot inside, for each of the 16 points inside the 2D elements. And this couples all the vertical levels, which in our problem were 128. We use the Newton method to solve this problem, and each step requires to solve a tridiagonal system. And it has a very nice structure. It's strictly diagonally dominant, which means that there's no need for pivoting. If you remember your linear algebra classes, the Lie factorization, the Gaussian elimination is stable for diagonally dominant matrices. That's very important because it allows you to pack the equations, which allows caching on CPU, and it allows to parallelize on GPU. This is one of the places where we use 2 different algorithms on CPU and GPU. On CPU, we use the Thomas algorithm, which is just a particular case of Gaussian elimination, which is optimal. And on GPU, we use the cyclic reduction, which is work inefficient but very parallel efficient method. It's a sort of a divide and conquer method. Each column residual is checked independently, which means that we allow for a different number of iterations per column. And we only solve 2 kernels for each nonlinear, full nonlinear solve for the whole system. So one for the initial guess and then one for Newton. And the scaling study shows a very nice scaling. Here the scaling is arguably perfect. I want to point out this graph does not include any MPI communication. So these are all just local kernels, which is why the scaling looks much better than before. I only showed a 3 kilometer benchmark here for all the 3 architectures and C++ and Fortran implementation. We observed that we are on P9, we're like a slightly better than the original implementation. On KNL, we're like much noticeably better than the original implementation. On the Y scale here is no longer simulated year per day, but it's the mean seconds needed for each Dirk solve. So this is something that Andrew Bradley developed at Sandia National Labs. The second thing that was important and the big challenge of the ultra high resolution is the high memory footprint. What this meant is that due to algorithmic differences as well as to the increased resolution, we had a much larger need for temporaries in our kernels. That meant that we had to pay a much more attention to how we allocated memory for temporaries. So Jim Fouker at Sandia developed this structure that takes care of allocating optimally memory on GPU. And it kicks in this thing, this workspace manager, as we call it, at high workload on GPU. And so if we look at the graphs on the right, the picture says more than 1,000 words. So those are 4 timers of home. The top left is the overall time stepping loop, while the other 3 are the 3 most important kernels. And the red line shows what happens when we enable the workspace manager. The blue line, what happens when we don't enable the workspace manager. The horizontal axis is the workload per node. This is a single GPU. And the y-axis is the columns processed per second. Thousands of columns that the code was able to process every second. As you can see, enabling the workspace gives a little performance hit on some kernels, on others is not noticeable, but it's limited. Like for the overall loop, it's less than 10%. It's about 10%, maybe a little less. But the most important thing is that you're able to fit larger problems on the GPU, which was crucial when we tried to solve the 1 kilometer problem on less than 4,000 summit nodes. When we tried to go on 3,000 summit nodes, without this workspace manager that Jim developed, we were not, like, the code would crash because it would run out of memory on the GPU. So this is something that we had to pay attention when we did our scaling studies. And even the tracer advection, which is the one that pays the biggest hit for having the workspace manager, has a penalty of about probably like 12. It's 5 out of 6 out of 40, so it's like 1/7. So something like 14–15%. Okay, so those were the results that I wanted to show you about our ultra high resolution, and then I wanted to briefly talk for the last 4 to 5 minutes about EKAT. EKAT stands for E3SM Kokkos Application Toolkit. It's the first name that we came up with, and we have never changed it, so it might stick for a while, but it might change. So anyway, so what is EKAT? EKAT is a collection of utilities, mostly related to Kokkos, that are useful across different, may be useful or needed across different E3SM related projects. We're currently using it in Scream to provide a few important data structure and algorithmic capabilities. The motivation is that several E3SM subprojects are gravitating towards use of Kokkos, either fully committed or at least as exploring the possibility. These projects sometimes are independent of each other in this Git sense, or they're different repos, but there's several common patterns that are needed across this project. So we implemented in EKAT some of this stuff. For instance, we implemented Kokkos-friendly structures for vectorizations needed on CPU. The tridiagonal solver that I mentioned when I talked about the nonlinear solvers, the workspace manager for temporary heavy Kokkos kernels, which I mentioned before, and then a few other utilities, including CMake goodies that help you maybe handle and configure Kokkos or unit testing. It is not a generic package in the sense that everybody can use it. The development is driven and sometimes tailored for E3SM needs. Nevertheless, I believe there's a few patterns that are probably common across different projects, which is why I wanted to bring this up. One thing was what we call packs and masks. So C++ has sometimes a harder time than Fortran to vectorize. I'm pretty sure we're all aware of that, especially when you have calls buried deep in the stack. Sometimes the compiler, if it cannot guarantee the alignment or compile the time dimension, it might have a harder time vectorize. So we developed, and there's not just us, several projects are doing this, develop like a structure for SIMD, for vectorization. The structure as a compile time length, which is usually linked to the vector dimension of the unit, the CPU that you have, although it could be a multiple of that, and then overloads a bunch of operators. But in Scream, we also have a lot of conditional loops, so we also added the mask structure, which allowed to do some operation, as I wrote in the example here. For instance, we can do overloaded power operation, which does a pack, so a vectorized version of the power function. But we can also update quantities in a masked way. So we, in the line out m equal blah, I build a mask where the pack 2 is greater than 1, and then I update pack 3 only on those quantities, trying to vectorize. So packs and masks have the two main purposes. The first is, of course, to enhance vectorization because of guaranteed alignment, compile time dimensions, and compiler vectorization directives where possible. But these are all hidden from the user, so you don't see a bunch of pragma here and there. You don't have the user to take care of details that are necessary for guaranteeing efficient vectorization. So when you read the code, it's much easier from the point of view of someone that is not very used, at the very least, to see a bunch of compiler directives and other stuff like that. Another utility that we have, for instance, we find it very useful in our unit test, since we're converting an original code from Fortran to C++, is the ability to do bit-for-bit reductions over a team of threads. This basically wraps the existing Kokkos implementation of a parallel reduction. But if certain flags are enabled, like I put here, like my bit-for-bit macro, what it does, it serializes the reduction. So this kind of does internally, like as a branch, and does two different things, either a serial for or a parallel reduction. But it's much easier from the point of view of the user to write a single instruction in your code that then has different behavior depending on configurations. And as I said, we have other stuff like tridiagonal solver and other utilities in EKAT, which we believe might be useful to other, at the very least, to other E3SM projects.
We're going to run out of time here soon. Just 1 minute more, and then questions.
I'm done.
Oh, go ahead. No, go ahead.
No, that was literally my last slide. I didn't. I just wanted to show like a couple of examples of things that we're trying to use EKAT for, like making life easier for a developer, as well as to making sure we achieve performance. And EKAT is also publicly available under the E3SM project GitHub organization. And with that, I'm gonna stop. And,
okay. We've got 2 questions that are in. Can you see those?
Yep.
If you can read the question before you answer it, that'd be great.
Sure. All right. Is there any plan for E3SM Scream to use single or mixed precision and gain additional speed up? Yes. So Scream is currently has a configuration option that can build either in single or in double precision. We haven't explored mixed precision, but I want to. I mean, we haven't really explored single precision a lot. We build and test single precision, but we're still in the process of converting the whole library. My hope is that when the conversion is done, then we can start studying the effect of solving in single precision, and the next step will be, well, let's solve just this parameterization in single precision and solve the other parameterization in double precision, or dynamics in double precision and, I don't know, microphysics in single, something like that. That's definitely something that we want to explore. Right now, we only have the support for either everything in single or everything in double, but the next step, the natural next step, is try to mix. Yes. Thanks for the question. The second question is, could you tell what were the main optimization in order to enable multi-GPU, multi-node scalability? Any insight on performance impact of NVLink versus PCI? We had a few iterations of our performance. I mean, when you run on these new clusters, sometimes your environment is as important as your as the optimization you do in your code. I wasn't the person involved in the large-scale simulation campaign. Oksana in our organization was in charge of that. She had a few back and forth with people at ORNL regarding how to properly set up the GPU Direct. But definitely there was an impact for when we use GPU Direct versus a standard copy to host and do MPI. Multi-GPU, multi-node. So yeah, those were the most important optimization that I think you were referring to. So Home is able to handle a GPU Direct, so use the pointer on device for MPI. Other optimization for multi-GPU, I can't think of any specific.